All right, parametrics. So parametrics, if you want to know about parametrics, you need to know about this guy. You know who that is? You don't know who that is? That's Mario. Oh, and his, with the disembodied head. And Mario in the old days was limited to 2 dimensions. So Mario could go walking, or he could run real fast. What else could he do? Jump. All these are possible for Mario because these motions are functions, right? What can't Mario do if he's restricted to functions? He can't go backwards, right? But Mario can go backwards. There's mathematical equations that allow him to go backwards, but how can it do that if we're dealing with functions? How can he, do this kind of thing? Well, oh, I like that little hop at the end. The way that he can do that is we break up x and y to cosine theta times some constant, and then sine theta times some constant. Now show me with your arms what cosine looks like. Goes up and down. Everybody do that. Cosine. How about sine? Just start somewhere else. Goes like this. But when you put them together, you can make circles, ellipses. You can do all kinds of things that weren't functions before, and now they are. This allows us to be able to do this kind of motion. So parametrics are important, and they're used a lot in programming. And when we do things like slope, all we have to do is we just have to use these parametrics. dy dx is going to be this function in terms of variable t, dy dt, divided by dx dt. So do you see how the dt's kind of cancel out? And so there's your dy dx. But that's how you find the slope. dy dt over dx dt. Now, this one's a little trickier when you take the derivative of this, but it's the derivative of dy over dx divided by dx dt. We'll look into that a little more, but this is the second derivative. This is the first derivative. Speed, we're going to talk about in a little bit, but it's the square root of the derivative squared plus the derivative squared square root. It's simply what? What does this look like to you? Distance formula. Change in x squared, change in y squared. That's all it is. So speed is at an instant is the square root of the dy dt, dx dt squared plus dy dt squared. Acceleration is in a notation you might not be familiar with. This is a vector notation that AP uses more than we do in IB, but it's these little brackets, second derivative, comma, of x and y. Now this one is the tricky one for position. Position of x of b and y of b. This is using calculus and using parametrics. This one's a little tricky. Here's what happens is that, let's say we're in position A and we want to get to position B. To find out what position B is in the x, you got to start out at position A, and then you're going to add the integral from A to B of the derivative of x of t dt. So all you're doing is you're taking dx dt, you're integrating it, going from A to B, and adding it to where you started. This is my start point. Okay, x of A, and this is my end point, x of B on the equation. Maybe it does something like this. So there's x of A, here's x of B. Now for y, it's just the same thing. Y of B is y of A, the starting point, plus the integral from a to b. What do you think this is of t dt? This is y of b, y of a. What do you think this is going to be? Y prime of t. So that's the formula for finding position. It's laying right here. So all of these formulas are right here for you. The only one that we probably need to go into more detail is the parametric arc length. And this is my absolute favorite. In calculus, what you can do right now is if you're at A, you're at B, and you have a function, f of x, what can you do with the integral of f of x dx going from A to B? What can you find? The area under the curve. Did we do that with Archimedes? Yep, and we did that with Riemann sums, and we did that with the shortcut. Okay, what I'm about to show you is different, is not the area, but imagine that string being stretched out. How long is it? This formula is not hard. In fact, it's quite easy. What you do is, let's say you have a spot I minus 1 and a spot I, and you have a curve. Well, you move over delta x, you move up delta y. Using the distance formula, it's the square root of delta x squared plus delta y squared. It's an estimate of that length, right? So if that's an estimate of the length, let's do a little trickery here. Let's say that the derivative of x is the change in y over the change in x. What's the derivative a shortcut for? What does it mean? Slope of a what? Tangent line. And what's delta y over delta x? What is that? Or change in y over change in x. What does that represent? This is slope. What's this? Slope. These are two ways of saying slope. Well, if we solve for delta y, do you see how I get f prime of x times delta x? So I'm going to slip this delta y here with f prime of x, that's this derivative, times delta x. And when I square it, I get delta x squared plus f prime of x squared times delta x squared. Now the square root of delta x squared is delta x. I pull it out of both of these, leaving 1 and f prime of x. This is what we call the length. Can you circle this one and this one? dy dx. This derivative is the same as dy dx. These are two unbelievable formulas. These are formulas that help you find a length of a curvy line of a function. We've never been able to do that before, but now we can. I'd use a calculator to do this, going from A to B. Last part. Parametric length. Let's say that instead of dy dx, we want to change this into parametric. dy dt over dx dt. Just divide both by dt's. And then dx, we're going to multiply by dt over dt. So this is dx dt times dt. And this is 1 plus that. Now what I'm going to do is I'm going to pull this into the square root, like that. And so now this was dx dt. Now it's the square root of dx squared dt. dx dt squared. Now when I multiply here, these are going to cancel out, but this is multiplied by 1. So I get dx dt squared, dx dt's cancel, leaving dy dt. So for a parametric, this is a formula for the length going from A to B. So one more time, you have L is equal to A to B square root 1 plus f prime of x dx squared. And then we also had A to B 1 plus dy dx quantity squared dx. And then this one is in terms of dt. So those three are formulas that you're going to use. for arc length. Yeah. Okay, so let's do an example of a BC problem, and this is good. At time t, a particle is moving x of t, y of t, and dx dt is equal to this, dy dt is equal to that. The initial conditions are x0 equals 0 and y0 equal -4. Those will come in handy. So what I'm going to do is I'm going to walk you through these four. The answers are already worked out, but I'm going to explain each one for you. You'll want to write these down. Find the speed of the particle. So I bet you remember that formula I gave you. Speed is equal to square root of x prime of 3 squared y prime of 3. So you would look at, oh, dx dt, that is x prime of 3, right? 4t plus 1. So if it's of 3, you'd put a 3 here. What will x prime of 3 be? 12 plus 1 is what? 13. So this will be 13 squared plus, now when you put in y prime of t, and it's the sine of t squared, you're going to put a 3 here. And now when you put in a 3, you're going to need your calculator. In which mode? Does this look like 3 degrees or 3 radians? Radians. So make sure you're in the radian mode or it's wrong. Okay, and so this is going to be the square root of 13 squared plus whatever the sine of 9 is squared. And then the square root should be 13.006, or 3 decimals, 13.007 is included. Did everybody get that with your calculators? That's not hard, is it? Love these. Let's do B. It says find the acceleration as well. Acceleration, you just take the second derivative. So if this is the first derivative, what's the second derivative of this guy? What's the second derivative of dx dt? 4, right? And then we put in a 3, but if you put a 3 and there's no t, this is just going to be 4. So the second derivative is 4, and then when you put the derivative of this, you got to do cosine t squared times 2t. You got a little work ahead of you there. But that's how you get those two numbers there. So 1 point for each of those, speed and acceleration. Find the slope of the tangent line. So we said that the slope is dy dt over dx dt. dy dt is sine of something cubed. And then dx dt is 4t plus 1. Now, if you're looking at it at 3, you put a 3 into each of these and divide them up, and you should be able to get 0.031. Just erasing through the rest of these to finish it off, you're going to do the position. Remember me doing that position? This is going to be x0 plus integral from 0 to 3 dx dt. Use that formula, integrate it, and then when you evaluate those, it's going to be equal to 21. This is going to be y of 0, which was given, plus integrate dy dt 0 to 3, easy, and then you'll get that. This one you'll want to use your calculator for sure. And then find the total distance traveled. That's my arc length. So for the arc length, it was the distance 0 to 3, dx dt squared, dy dt squared. You put that in your calculator, and you integrate it, and you'll get 21.091. It is 1 point for writing this out, and 1 point for the answer. So you got to make sure you have both. And that is parametrics with the BC calc. You're going to do just this problem for tomorrow. So go ahead and try that. We'll go over it. And then as many of these multiple choice as you can. And I think there's a total of 7. All the answers are given.